So in this session of discussion, we'll discuss on the characteristics of field effect transistor, uh, which is the second section of the module 2 of your syllabus, that is of Mumbai University. Fine. Contains, will determine the characteristics, output characteristics. Not only determine means we'll be plotting them by knowing some values of the output voltage VD and ID. Then various configurations of JFET. These are namely self-bias, various configuration of junction field effect transistor. First one is in the active region. Second one is in the cutoff region. Third one is a saturation region. Self-bias circuit of junction field effect transistor. Numerical based on self-bias. Numerical includes analytical as well as graphical approach of self-bias circuit. Then graphical approach to set a Q point. Second biasing of a field effect transistor is the voltage divider network. Third one, numerical based on voltage divider. And lastly is the application graphical method to Q point. Last is the application for the biasing circuits. So most important thing to remember over here is that for n-channel FET, the maximum current flow is ID when VGS is equal to 0 and drain to source voltage is VP. For gate to source voltage, VGS is less than or more negative than the pinch off level. The drain current is 0 amperes. And for all level of VGS between 0 to pinch off level, the current ID ranges from maximum drain current to 0 amperes. Whatever are the conditions we have studied for N channel, same thing is applicable to P channel FET. So various states of junction field effect transistor. Here this particular circuit is working in active region. So the identification of junction field effect transistor in active region theoretically is VGS is equal to 0 and ID should be equal to the maximum amount of current flow when the drain to source terminal is larger than the pinch off voltage. Second situation, when the configuration attached connected is in cutoff region, we can say that the given circuit is in cutoff region when your drain to source voltage is equal to VDD or which is lesser than VP, and the drain current flowing is 0 volts. Third configuration is the saturation region, where we say that the voltage between the drain and source terminal is very larger than the pinch off level and gate is made negative, due to which the current becomes 0 and it reaches to maximum when VGS is equal to 0 volts. So transfer characteristics. Transfer characteristics are defined as output current versus the input voltage, and this is very relatively related to the input output characteristics, that is, which is plotted by taking the parameter ID and VDS, keeping the parameter VGS to some constant value. So in this case, when VGS is equal to 4 volts, that time the drain current is 0. VGS is equal to 3 volts, that time the drain current happens to be 0.5 milliamperes. When VGS is 2 volts, that time the maximum drain current is 2 amperes, and when VGS is equal to 0 volts, the maximum drain current that is flowing is 8 milliamperes. So all these plots what we have seen or talked about are very closely related when you are plotting the transfer characteristic. So in this case, when VGS is 0, maximum drain current flows, that time your mode of operation of junction field effect transistor is in active region. When VGS is negative and ID is equal to 0, that time it is in saturation region. So in this way you can plot the transfer characteristic, and ID versus VGS is closely related by this relation which is called as Shockley relation. So derivation of Shockley relation, next slide. Shockley relation is given by ID is equal to IDSS into 1 minus VGS by VP whole square. So apply the condition when VGS is equal to 0, ID is equal to IDSS. Fine. This is one point. So coming to the output characteristics or the transfer characteristic, when VGS is 0 volt, that time IDSS is maximum. So in our present case it is 8 milliamperes. Consider a second case when VGS is equal to VP, that time ID is equal to 0 amperes. So in our present case it is 4 volts and current ID is 0. Consider the situation when VGS is minus 1 volt, that time the current obtained is 4.5 milliamperes from the graph here. The fourth case, when VGS is minus 4 volts, that time maximum drain current can be yielded. So comparative table, when how is VGS related to ID? When VGS is 0 volts, that time maximum drain current flows. And when VGS is maximum, that time the drain current is 0. So it is showing the relation that they are inversely proportional to one another. Definitely, because a resistance, which shows that some resistance is appearing in the device, which is termed as a dynamic resistance. Right? Next, we'll see some about the junction field effect transistor biasing. We'll consider the two biasing, self-biasing and voltage divider biasing. So analyze the self-bias circuit, calculate the currents and voltages in self-bias circuit, set the Q point of the bias circuit, graphically analyze the self-biased circuit. Then second biasing circuit is the voltage divider biasing circuit. Same things will be repeated in the voltage divider biasing circuit. We'll analyze it by finding the current and voltage, and at the same time analyze it graphically by setting the Q point on the voltage divider bias circuit. Then graphically analyze the voltage divider bias. So self-bias circuit, in this case, your RS is connected. This whole circuit, self-bias circuit, is comparable to our emitter bias bipolar junction transistor. So for N channel, IS is equal to ID, VGS is equal to 0, VS is equal to ID RS. Get to source voltage. It is a difference between the gate voltage and the source voltage. So in our present case, VGS is 0 and VS is minus ID RS. IS is equal to ID. That is why here IS is taken to be ID. So this is equal to minus ID RS, which shows that our biasing circuit VGS is negative. Self-biasing circuit for P channel. Here the polarities are opposite. VDD is negative and source current is flowing into the source terminal. So P channel VGS is ID RS. Since ID is equal to IS, we say that it is ID RS. Then drain voltage with respect to ground. Drain voltage with respect to ground is VDD minus IDRD. So because VS is equal to IDRS, we can establish VD. Numerical. So for a particular junction field effect transistor, the circuit is given. Parameter values such as transconductance, get to source voltage, maximum get to source voltage, and the drain current is 5 milliamperes. It is given. We have to find out if this transistor, if this junction field effect transistor is replaced by another transistor, will the overall scenario remain the same? So given the drain current as 5 milliamperes, and if it is replaced by another junction field effect transistor which is in working condition, will produce the same result in the circuit due to variation in the parameter values. So find out what are the required set of values for the given for this given configuration with this junction field effect transistor. So Vs is equal to IDRS comes out to be 1.1 volt. Vd is 10 volt. Vd here. Vd is Vd with respect to ground. So Vd is VDD minus IDRD. Then find out drain to source voltage, which is equal to VDD minus Vs, so 8.9 volts. VGS is given to be 0 volts. So VGS comes out to be minus 1.1 volt. So whatever are these values calculated for this given junction field effect transistor, if it is replaced by another field effect transistor, will these set of values remain same? So determine the values of RS to a self-biased P channel junction field effect transistor. and whatever are the values given here, they are taken from the data sheet. So ID is equal to IDSS into 1 minus VGS by VP whole square, which comes out to be 11.1 milliamperes. When RS, we have to find RS. RS is nothing but VGS upon ID. So RS is 450 ohms. Graphical method. The whole configuration cell bias circuit is given. Its characteristics are plotted. So here in this problem, the transfer characteristics will be given, and you have to set the Q point by various locations. Which will be studied in the incoming slides. So graphical method to determine the Q point. First we have to remember this, the curve for a required configuration can be acquired from datasheet. If not available, take the values of IDSS and VGS from the datasheet and plot the transfer characteristics. So this was the problem that was given in the third slide from the present slide. So we have to plot this characteristic. So determine the Q point. So when VGS is 0, we get the maximum drain current. Fine. So this establishes this particular point. Second point, when VGS when ID is equal to a maximum value of 10 milliamperes, what will be the value of VGS? So it is equal to 4.7 volts. That point we have to consider. Thirdly, the point where the load line intersects the transfer characteristics is at 5 milliamperes and minus 2.3 volts here. Second biasing circuit, a voltage divider bias circuit. So this is again an N channel FET. ID is equal to IS in the given condition. So voltage divider biasing circuit, Vs is equal to ISRS. Since IS is equal to ID, this will be referred as ID into RS. Voltage Vg, apply a voltage divider rule across this network, VDD R1 R2. So Vg is equal to R2 upon R1 plus R2 into VDD. Get to source voltage, it is the difference between the two voltage at the gate terminal and the source terminal. Source voltage, so it is a difference of Vg minus VGS. Drain current ID, it is Vs upon Rs. So if we substitute the value of Vs is as Vg minus VGS, we get the relation as ID is equal to Vg minus VGS upon Rs. We'll solve a simple numerical on voltage divider bias circuit. So in this circuit, what is given is a bare value of the minimum value of the voltage Vd. These are the components that have been selected for working out of this circuit. We have to determine the current ID and VGS. How do we go ahead? So minimum drain voltage is given to be 7 volt. Corresponding to this, you find out the drain current ID. So it is VDD minus VD upon RD, which comes out to be 1.52 milliamperes. Now to find out the value of get to source voltage, Vs, first we have to find out Vs. I mean, Vs over here, which is equal to ID into Rs. This comes out to be 3.34 volts. Second step, you find out Vg. Apply a voltage divider rule. So Vg is equal to R2 upon R1 plus R2 into VDD. Substitute the values of R1, R2 and VDD. So it comes out to be 1.54 volts. Lastly, you take a difference of these two voltages, Vg and Vs, and find out Vs, which is minus 1.8 volts. So when VGS is negative, it certainly shows that this given configuration is in the active region and it is working in a linear region. Suppose if the voltage Vd or the drain voltage would not have been given, it would not have been possible to set the operating point. That means we wouldn't have been able to identify whether the given biasing circuit is in a stable mode of operation, that is linear region, or it is in non-linear region. The idea behind determining the stabilities of the amplifier or defining it in linear or non-linear is that we should get an accurate response at the output, amplified response, and not a clipped signal at the output. So therefore, the if a circuit is to be operated as an amplifier, it has to be stable, working in linear region. So graphical method. Here follow same way. In our given problem, this characteristic is given, transfer characteristics is given, and we have to find out whether the Q point by using a graphical method. So step 1 again go same way. When ID is equal to 0 and VGS is equal to 0, first point we get here, fine. When ID is 0, VG is this much, VGS is equal to VG. Second point, when VGS is 0, what is the value of ID? So ID is VG upon RS. So this is the second point. Plot these 2 points, you will get a load line which is having a slope of VG by RS, and this determines your Q point, which is the operating point of the linear amplification device. Application. Last slide. Here I'm trying to give you the application of an wastewater to determine the pH level of this wastewater. So here this is a sensor, fine. This sensor will sense the quality of the water. So water is made to flow across this. Based on this, there will be variation in the gate voltage. Here there are two gate terminals, G1 and G2. So the variation of the pH sensor is applied at gate 1. At gate 2, the voltage divider network is applied, where it will decide the biasing, gate biasing for this voltage divider bias network. And here we can vary the VDD, we can vary the drain voltage, and accordingly this VG will vary, and it will be comparing with the gate voltage of this, and it will define the output voltage. So this output voltage is comparable with the pH level of the wastewater, and it will help you to determine whether the water impurity is alkaline, acidic or neutral. This completes my presentation over here.